Okay, welcome back.
It's one example of unpredictability.
Yes, exactly. Right. Examples of unpredictability. Well, actually, did anyone come up with examples? Right, that's the homework assigned Tuesday, next Tuesday, of everyday examples of unpredictability. Yeah.
So how about the day that my roof is going to start leaking?
I have one of those roofs too. And up in the attic, I have blue tarps underneath the area that gets wet. So, yeah.
Well, it hasn't started leaking yet.
No.
It's like 30 years old, and it's, you know.
Yeah, exactly. Yeah. Well, mine is leaking. I just have patched it, and I go up after 3 days of rain. So here's the part that's predictable. I know that after 3 days of constant rain, we occasionally get these. So some years this is not an issue. I go up there with my little wok giant spoon and a bucket and scoop out from the. So that part's predictable, right? And this directly affects my life. In years past, I have woken up to the drip is right over my bed. Drip, drip, drip. And the dripping is quite predictable. In fact, when I was a grad student down in Santa Cruz and we were first studying some of this chaotic behavior, one of the first systems we studied was a dripping faucet. And a dripping faucet can be chaotic. Now, of course, the mode that drives you crazy, if you're trying to fall asleep and your bathroom door is open and the gasket isn't good, is its regularity, drip, drip, drip. But if the valve isn't too corroded and you have some spare time, you can try increasing the flow rate a little bit, and it'll go from drip, drip, drip to drip, 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 drip. It takes 2 drops to repeat. If you're really patient, well, actually you have to go down and buy like a really fancy flow control valve and set up an experiment, and you fiddle a little more, it goes, well, I can't really do this. Drip, 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 drip. 4 drips. So we're going to study something called the periodic route to chaos, and dripping faucets actually exhibit that route to chaos. And behavior gets complicated and eventually is sort of overtly hard to predict through this series of what we call bifurcations, where you go from drip, 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 the time between drops is constant, to the repetition takes 2 drip times, so there's a short time and a long time, and then so on, up to 4 and 8, 16, 32, with smaller and smaller variations in the flow rate. So any other examples of predictability?
While we're on faucets, my apartment complex, we share a water heater.
Yeah.
So when you turn the hot water on in the morning in the shower, and you have no idea when somebody else is going to turn it on, you're going to get cold water, or and then you turn the cold off so it's warm again, and then somebody's going to turn their hot water on, and so you get blasted. And,
Right.
and you get hot and cold.
Right.
Unpredictably.
Yes, and so here we have sort of really complicated systems where you have these components called human beings involved. And human beings are strategic, right? I can kind of hear the way you're describing this. And like, oh, maybe I should get up a little bit earlier. Oh, it's too cold out. Oh, I really should get up. You know, do I want hot water or not for my morning shower? So this is not a course in game theory. However, there are some of the tools we're going to introduce using nonlinear differential equations and dynamical systems modeling have been applied to game theoretic situations. So, for example, you can imagine 2 agents where the game that we're playing and the reward interaction, the rewards that drive our game choices, is, say, rock, scissors, paper. Okay? And you can make a little model, dynamical model, that I have a strategy, which is just the current probability that I'll play rock, scissors, or paper, and you have the same, an internal model, if you will. And you can write down adaptive equations that end up being a set of nonlinear differential equations where there'll be things where we're both playing papers, but we don't like it, so we start playing scissors and I start playing paper. Well, then I start losing. I don't like that. Therefore, I start playing rock, but then you start losing, right? And then you start playing, and so on. And so you actually get these cycles, periodic behavior, but also as you change the detailed structure of the rewards that you're getting for different plays, the system can become chaotic. So that would actually make a good project, by the way, sort of game dynamical systems. So, any other examples? Yeah.
the wait time and even the fact whether or not your job actually goes through on enough department printers.
Oh yeah, right. Yes, right.
So
Yeah.
maybe also against the article, but since the printer queues don't really work, there's really no information there at all.
Yeah, right. Yeah, queuing systems generally, that's true. We're certainly waiting for the printer. And if you're in the same room, I used to teach a class over in the undergrad computer lab.
Yeah.
And of course, if you hear someone printing out a big job, you usually wait because, maybe you should just go to a different room because they're printing out the C++ manual or something like that. Or discount tickets for a Tahitian vacation. You don't know what they're doing. So, yeah. The queuing systems generally, probably the most important queuing system we know it's chaotic that we're using right now is the internet. So there are these boxes that are sort of the hardware substrate of the internet called routers. And we go buy sort of off-the-shelf routers from Best Buy and whatnot. But the real workhorses are these rather large computers called switches, switching routers that Cisco and other networking companies make. And one of the very interesting things in the early days of the internet was the fact that, well, you went down to Cisco, and if you were a communications engineer, you plopped down your $50,000 to get the Cisco fancy router in 1992. And of course, the reason you bought that is you were looking at the spec sheet. It said 250,000 packets per second. Oh, that's good. Of course, if you paid 100,000, it would double it. But anyway, so you bought the 50,000. But now you deploy this. And eventually, right, the whole internet was done by individual people making these buying decisions. We're putting together these Cisco routers. And what would happen, over the entire US, the throughput would suddenly drop to about 10% capacity. And it would slowly climb back up over about 5 or 10 minutes and then drop again. And it started doing this called internet route flapping. There are actually a couple different reasons this happened. One that I just mentioned was the Cisco routers wanted to make each individual router kind of adaptive. So they have a way of talking to each other. And they say, oh, Freddie over there, router Freddie, what does your local neighborhood look like, and where's the traffic, and where are things, where's there good bandwidth? So they have kind of a semi-local map, and they talk to each other, and they exchange this map. Well, then you have to decide what to do with it. So what they had done early on, the smart thing they thought was to, oh, it's busy over here, I'll send the packets on this route. Well, all the routers were using the same control algorithm. So everyone switches to use this route, and suddenly that's busy, and now this other part is not busy. So switching back and forth. So trying to make it intelligent actually made it more chaotic. Hard to predict. In this case, it's shutting down. There were these huge waves that would kind of propagate back and forth across from coast to coast. And it took them about 6 or 9 months to figure out exactly what the mechanism was. Right? It's like, wait, here's my individual box. I designed it so it does 250,000 packets per second, right? It's like, no, that box behaves in the context and becomes coupled to other boxes in a non-trivial way. And that's kind of the lesson of these nonlinear dynamical systems. We're looking at systems where thinking of the group behavior in terms of a sum of the individual components. Right? That view would have said, oh, I have 10 routers and each doing 250,000 packets per second. I can do lots of packets. Here, there was a control protocol, a separate channel that was actually modulating things and causing it to go unstable and then actually shut down. So, any other sort of thoughts of examples, everyday experience of unpredictability? Yeah.
I guess the failure of the running software system.
Yeah. Yeah. Right. So there's sort of different ways to think about that. So right. So the example is the way an operating system runs. That's a kind of a little, the different ways they're hard to predict. That's for sure. There's sort of this dichotomy between, I don't know, how many of you have taken computer science courses and taken, say, a compiler design course or something like that. There's this kind of, kind of the engineering attitude toward these things, kind of like Cisco designing the routers is, oh, I'm going to design the language, and I'm going to write an algorithm, and gosh darn it, that's deterministic. It does this statement, and this statement, and this statement. The problem is that kind of design paradigm doesn't extend to what we have now, is we take these locally deterministic things. Well, there's even an argument there. But let's say they were deterministic and kind of idealized, but then we couple them together. Not only to each other, but we have these really complicated systems that we couple them to, called human beings, right? So suddenly there's all of this tremendous amount of unpredictability. You know, it's almost like the deterministic part of these machines is the least relevant for looking at sort of long-term behaviors, because they're all interacting with each other. Human beings do different things. So, we put varies on that word. Yeah. Any other examples?
Also, I think another example is the outage of power grid.
Power grid, right?
Yeah.
Yes, right.
It's very complicated.
Right, right. So one of our colleagues in this Complexity Sciences Center, Raisa de Sousa, she studies power grids and transportation networks. And there, she teaches a very nice series of courses on that. And they're examples of nonlinear dynamical systems. A lot of the work there tends to look at the topology, the communication structure, and ask questions like, say for a power grid, if I have a tree fall over in Oregon, you know, how likely is that to affect Southern California? And there was a very large power outage that was exactly that happened maybe about 15 years ago, cascaded all the way down to Northern California. And with just one power line, one branch falling across that, but then of course, it kind of echoes a little bit like this internet route flapping. The power managers at the station, oh, that line is down. In fact, some of this is automated. That line is down, I'll shift the load over here. Well, these lines have load capacities, and if you exceed that load capacity, it fails. And then you shift the load over here now, and that fails. You get these what are called cascading failures going through. Very much, the structure of that, how these things avalanche, how the failures cascade is determined by the topology of the network. So there's a lot of work now trying to understand how the structure of the network can help isolate failures like that. Bottlenecks. Yeah.
We had it more recently in New England.
Yes, that's right. It's a big failure. And then right, kind of middle central northern U.S. Yeah. The people still working on this. Yeah.
Yeah.
I think the most fascinating one more recently is the flash crash from capital markets with algorithmic trading.
Yes, very much so. Yeah. Yeah. Yeah, there are a lot of interesting stories about that, right? One, maybe somewhat apocryphal, is that MIT was very early on kind of an innovator in developing a graduate program in financial engineering. And lo and behold, rather than taking physicists and engineers from NASA when they shut down some space program, moving them to Wall Street, there was now a formalized program. And of course, these students all took the same classes, and they learned the same algorithms. How to price options, selling Black-Scholes partial differential equation for option valuation, all learning the same things. So what do they do when they get hired? They write all the same code. Right. So one theory about the flash crash, and a couple competing theories, is that there was a certain sort of structured downturn, maybe just caused by some fluctuation in pricing, market's noisy, that was recognized in different companies by the same software, essentially the same software, and they all acted the same way and started dumping. And so within about 3 hours, right, you had this 1,000-point drop in the Dow. Oh, $2 trillion in wealth, just like that. Right? So you start thinking about this and you realize that's a problem. Right? Look at me. I mean, I've got all this technology. Right? We love technology, and we build networks, financial networks. We're building political systems. We're arguing for global trade. But all of that is coupling systems together, non-trivial systems and coupling together. And then we whine, complain when they crash or they go unstable.
But then there's the argument that they're more stable because they're coupled.
Well, right. Well, and then then there's this issue: how do we start to analyze these systems such that we can predict where the instabilities are, anticipate that, and maybe add in some stability? So we're not going to address very large social technical systems, but the ideas in the course will give you some glimpse about the ideas that are available now and start to see some of the mechanisms that lead to these instabilities. What is instability? What's stability? how to quantify those things and how to measure and detect. Almost you could think of where our use of information theory would be to develop diagnostic tools to automatically monitor systems. Right? The power grid has dozens and dozens of power stations, Western States power grid, dozens and dozens of power generation stations. And there are people sort of sitting there, but what you need is someone who has a global view. Well, the global view is very problematic because there are dozens and dozens of variables that you have to monitor. And how can you picture that in your head? So we need some way of looking at the intrinsic behavior and having some kind of statistic, some sort of monitoring or diagnostic system that reports back compressed statistics that human beings are capable of understanding. And to do that, we need a theory of instability and stability, ways of quantifying those things. So that'll be one of the themes of the course. So how many people read the Lem article? A few. Any thoughts on that? I mean, again, that's just mostly amusement. I like the way he writes, right? I mean, it's very ironic. Actually, in past years, some people have found it annoying, but I find I enjoy his style of writing. So as you can tell, he's science fiction writer, Polish, passed away about two or three years ago, but obviously knows his probability theory enough to develop that kind of philosophical critique. And always very absurd, right? Either life doesn't exist or the theory of probability is wrong. I mean, it's like, okay, what are we doing here? So,
Yeah, well, when I was reading the article, what it made me think of is all of those arguments about how at the moment of the Big Bang that certain
Right.
parameters needed to be set.
Right.
And if we weren't here to observe them, we wouldn't even be asking or thinking about
Right.
it. That it's like, whatever got set, that's, we wouldn't be here if they weren't set that way.
right, yeah. And he paints a nice picture of this just exquisite contingency of everything, right? And so what allows us to then talk about typical behavior? Everything is particular, right? I mean, how do you, there's sort of built into one notion of probability that it is how often something occurs. Well, if every particular state of the universe is its unique thing, there's no notion of ever repeating that, right? So anyway, it kind of exercises some of the philosophical problems with thinking about probability. But we'll have to deal with that, because we're going to deal with nonlinear systems that actively produce what appears to be probabilistic, stochastic behavior. So, anyone look at the Scientific American article? That's mostly just kind of an overview of the nonlinear dynamics we'll cover. Again, just a few pages give you some sense of the ideas, the historical role, and a number of the figures in there we'll come back to. We'll do some in-class demonstrations of these mechanisms of chaos. But what I want to do is a physical demo. Let's see how this works here. Oh, not too bad.
It can't be seen from the projector head. Projector head is right in the way. So I think if you angle it or something,
Just rotate it.
turn.
Projector. Oh, this head.
That,
Yeah.
yeah.
Let's see. How's
That works.
Oh, really?
Yeah.
Okay. Always things to anticipate. Okay, good. So, actually, set this up again. I carefully calibrated this last night, but just rolling it in here. So what do I have here? This is just a simple pendulum. There's a pendulum bob that has a magnet in it. And that magnet is attracted to each one of the magnets I've attached to the top of the overhead. That's nice stable behavior. Oscillating periodically, very nice. So the reason I like doing this demo, there's even kind of an unstable equilibrium in the middle. is that as the course develops, we're going to be making some excursions into fairly abstract stuff. So the questions we were just talking about are kind of easy to motivate and understand intuitively. And of course, I wouldn't be sort of having us discuss these things if there weren't some constructive solutions and ways of thinking about this. But we're going to have to make some excursions into mathematics. However, she always, as we're doing this, like, why are we studying this weird geometric stuff, topological stuff? Keep in mind these examples we were just talking about, and this simple physical pendulum. Right? As we develop these abstract concepts, they're always being related back to some even very simple system like this. So this is not a complex system. This is not the internet, right? You know, if you were, taking graduate classical mechanics, I could make this your problem on your qualifying exam. Right? I would ask you to write down the Hamiltonian and explicitly write out the equations of motion for this. Right? It has a certain number of degrees of freedom. Right? Degrees of freedom means what? Well, assuming that the rod attached from the suspension to the bob is rigid, then we really just have positional information. So we have, right, the pendulum bob is constrained to move on a sphere. So we have to specify two numbers for that. Maybe you could do angular coordinates, your choice. And then, of course, Newton tells us that mechanical systems, we also have to worry about their velocities. So for each of those two positional coordinates on this sphere of locations, you'd also need a rate of change. So this is a four-dimensional system. Okay. Oh, which is to say, simple. So, like I said, that's nice simple behavior. You can kind of imagine, if you knew your Fourier analysis, studied your simple harmonic oscillator, you could kind of imagine describing that periodic oscillatory behavior. And of course, it slows down because there's air friction and friction in the support. Okay, so this would be like a dissipative simple harmonic oscillator. Okay, now what I'm going to do is just start it off here, move it away from the magnets, and just let it go. It'll slow down because of dissipation. So now even the large-scale behavior, that's nice and predictable, right? Regular, again, you could imagine making some approximation with a periodic simple harmonic oscillator. But at some point, it deviates from that and ends up with this very complicated sort of trajectory. Okay, so now it's settled down on this magnet. So now what I'm going to do is very carefully start it in exactly the same initial condition. Not, but close. I'm trying to be close here. So now place your bets. You laugh. But in fact, this is sold as a game of chance. Oh, how many predicted that? Well, you have four magnets, so at least you can say, quarter probability, and you vote for it. Okay, so let me press my luck here. Okay, same initial condition. Ryan wants this one. I'm gonna go for this one. Ah! Almost around this one. Okay, what's going on? This is a simple system. And what you just saw before your very eyes is unpredictability. What's going on? So much of the kind of model that we do in science is assuming that systems are predictable. Or if we're engineering a system, we want its behavior to be predictable, form a certain way. But even the simplest systems, nonlinear, can be chaotic. So I'll pass this around. You can see it's a little tattered. I actually bought this game. It's called Gyration. You notice we're having cocktails and gambling chips over here, cigars, bracelets, and so on. Very elegant circumstances. I bought this in Piccadilly Square in London. A friend of mine, Michael Berry, father of the berry phase and found this toy. They don't make them anymore.
They
Poor substitutes.
yeah. They
Poor
have
substitutes.
plastic ones now
Yeah.
with multiple magnets.
And then in the game, you're allowed to sort of make the magnets attract or not attract the bob and so on. So they kind of then. Okay, so again, as things get abstract or a little bit complicated, you're having difficulty, always keep in mind we're trying to understand very simple systems. Now, complicated behavior in simple systems. So there might be some time we do some long sojourns into abstraction, but it's all to come back and to actually explain the mechanisms that somehow are expressing themselves in this complicated behavior. Right.
So that's chaos.
This is, okay, yes, this is chaos. In fact, what it's called is transient chaos. Right? What I can predict is that because of friction, it will settle down and stop on a magnet. I can't predict which magnet. And in particular, through the transient chaos, you can start to see visually the actual trajectory that was doing, that was very complicated thing. And, you know, maybe, I don't want to make this too mysterious. What's going on here to a certain extent is that pendulum bob is attracted to the four magnets, and there's kind of a competition between them. Pull it this way, pull it this way, and that sort of keeps going because of the momentum of the bob. So it's kind of moving through between these four competing forces, and that very competition is taking small variations and kind of magnifying them into this complicated trajectory. Yeah.
So is this really a case of truly unpredictable, or merely that our limits of measurement and
Right.
computation
Right.
are exceeded?
Excellent question, and we are going to answer those. Each one of those is a contributor to this. Right. So initially, we're going to focus on these nonlinear dynamical systems to kind of understand how intrinsically, in their state space, how the nonlinearities in their equations of motion produce complicated trajectories. But then that also couples to the accuracy with which we measure something. So I was, kind of pretending to start in the same initial condition. I obviously couldn't control that experimental initial state so carefully. So there's a certain amount of control uncertainty. And it turns out that this complicated, chaotic, dynamical behavior takes small uncertainties and amplifies them. So those uncertainties can come from I can't control the system, I can't measure it accurately, and any small, even epsilon small, I'll convince you, even epsilon small uncertainties in measurement or control will lead to that small uncertainty amplified to macroscopic, unpredictable behavior. Now, there's kind of a more general notion of ignorance, which is I don't even know what the equations of motion are. Right? Maybe you don't know what model to put on your computer to simulate this. So we'll also talk about, mostly in the spring quarter, sort of what happens with with modeling uncertainty. I don't even know what the right equations of motion are. So yeah, go ahead.
We lost your video.
Call recorder warning.
What? Oh, sorry. Okay, so back to more normal mode. So that's the sort of motivations for studying this area. Goes by different names: dynamical systems theory, or qualitative dynamics. Part of this is trying to analyze these nonlinear systems without solving the equations of motion. And the main set of techniques was introduced by this French mathematician I mentioned Tuesday, Poincaré, in the 1890s. Sort of the grandfather of the whole area. It's now actually quite a large field. And the reason, kind of a practical reason, that we need techniques other than calculus directly solving the equations, that most of these nonlinear systems the solutions can't be expressed in closed form. So we'll give you some examples of that. Are they still on?
Yeah, we are, Jim. I just turned off my video.
Oh, okay. Good, thanks. Can you see me?
Yeah, we see you fine.
Okay, good. I'm not seeing my little head dancing around, but that's fine. Okay,
there.
sorry.
Do you want me
Okay, so
increase I can increase the picture-in-picture.
no, that's fine. So is that centered on the slide?
This slide's
Okay.
a little off, so it can see you also.
Okay.
Sometimes.
I'll stand over here.
Yeah.
Well, so what are we gonna do? What alternatives we have if I'm not using my first and second year calculus to solve these differential equations? What alternatives are there? Well, one approach would be to just use statistics. Right? We're already sort of talking about, even with this mechanical system, whose deterministic equations motion I in principle could write down, or physics grad student could write down. We were already discussing this probabilistic behavior on which of four magnets the thing ended up on. So why not just say, oh, I'll just use statistics, notions of probability. Great, right? And we will. Another approach would be just to take the equations of motion and code them up with various efficient differential equation integrators and compute the solutions. Great. Okay, so that's one approach. Then there's the mathematical approach, which is what we're going to sort of emphasize. But we'll use all of these things. Now, there are problems with them, right? To say that I'm just going to look at Pendulum and just describe its long-term behavior and uniform probabilities of reaching the four magnets, that obviously is a very impoverished description. Right? We saw there's a complicated trajectory. We'd like to know what's producing that complicated trajectory. To just say, 25%, 25%, 25%, 25%, throws all of that out. And that's sort of a general characteristic of using statistics. You're throwing some of the microscopic or more detailed information away. Often you want to do that. Maybe there are questions you have, right? You and I are gambling at the bar and we're just betting on which magnet it goes to. Okay, that's all that really matters. And you and I exchanging a discussion of complicated trajectories over martinis is maybe not the point, right? So what about doing simulation, numerical simulation using computers? Well, actually, we can actually write down the models and simulate them. But to the extent you might say, okay, great, I can use a computer simulation to actually predict the behavior. But it turns out, again, this sensitive dependence on initial condition, the sensitivity on errors in knowing the current state of the physical system and being able to control it means that even the simulation won't start off in exactly the same place that the physical system did. So you kind of imagine them kind of running along, and eventually they'll deviate. Also, and this is an argument I've gotten with many, many people, to write a computer program is not to write down the theory that helps you understand why something works. My stance towards using numerical simulation, it's more like the computer's very powerful. We can actually run big models now, right? Climate models, all that. They're more experimental systems than they are tools for direct understanding. And it's really the ideas from dynamical systems theory that let us start to give a mechanistic picture. We have to introduce new concepts, a new kind of vocabulary that explains what these mechanisms are. But it's really the mathematical theory of dynamical systems that helps us start to understand. But when we study these nonlinear systems, we use all of these tools. No one is preferred. In fact, even dynamical systems theory, it has certain limitations. It makes certain assumptions about how it describes dynamical behavior that also need to be extended. So all good, but they work together, these different approaches. So we're mostly going to first talk about dynamical systems theory, look at some of these nonlinear systems, just to get some sense of how rich, how bad can it be out there, how rich behavior can these nonlinear systems produce, just to give us some sense of what's inside that gray box. And then we're going to shift over more to, we'll do some simulations. We'll get to play with these various kinds of so-called strange attractors and look at their geometry and so on. And then we're going to shift over more to an observational point of view where we're trying to measure them and predict them. We're going to ask for quantitative measures, so kind of shifting into a statistical and information theoretic view is a way of being precise about measuring how unpredictable these chaotic systems are. And how that quantitative measure of unpredictability is related to the complicated trajectories that these systems produce. So, okay. So I guess with Tuesday and the preceding comments, I've been doing a lot of sort of hand waving and trying to motivate these ideas. So now we actually have to roll up our sleeves and get down to work. So here we go. So here's finally some of the concrete ideas here. Okay, some of the mathematics. Again, it's it's all oriented towards thinking about complicated behavior in the real world, or in engineered systems for that matter. Okay, so the most basic assumptions that dynamical systems makes about some process or system out in the world is that there's some state space. So I denote that with calligraphic X here, artist's conception of a state space. So what do I mean by state space? It is the set of all possible configurations of the system you're interested in. So now let's think about that pendulum. What's the state space for that pendulum? I kind of talked through it a little bit, right? So the first thing was, okay, kind of listening, remembering Newton. So this system has positional information, which I argued because the rod was rigid, that the positions were constrained to be on a sphere, two-dimensional sphere, okay? So a point on a sphere is defined by two numbers, okay? It could be angles or XY position if you wanted to. But then also we had to worry about velocities. And the velocities are unconstrained. They can be negative or positive and basically any magnitude. Not very large when I was doing it here, but in principle it could be. So the state space, as I said before, for the pendulum was four-dimensional. Each state is a vector of numbers, four numbers, two angles, or two numbers to indicate the location on the sphere, and then two velocities, the rate of change of those two positional numbers.
Question about state space. It seems like just kind of how you said it, it seems like it might be a little subjective because if we don't have Newtonian mechanics, then
Right.
we may only think of it in terms of position.
Right.
And then each state is kind of probabilistic as to how
Right.
it's going to evolve.
Absolutely, yeah.
And I don't know. I guess is that kind of true in general? That states are more just how you look at it than the actual system itself.
Oh, the description I just gave you of that pendulum, I totally pulled the wool over your eyes. You say, absolutely not. I know that the metal rod is made of atoms. There's a plastic sphere. That's made of atoms, molecules, polymers. It's a huge dimensional state space. So, shouldn't take the things I say at face value. and who's to say that that's not a better description? It's pretty complete, but I kind of argue it's, depending upon the question you're asking, which magnet is the bob going to, maybe you don't want to have a model of Avogadro's number of degrees of freedom. Why? Because most of them are kind of rigidly coupled together.
Superfluous.
You might, or maybe a little lighter, kind of irrelevant for the question you're asking. So I'm actually giving a positive answer to, yes, there's a kind of subjectivity. But it's not a negative kind of subjectivity. It's the sort of thing, every time you approach a new system, you have to ask these questions. Now, there is much more principled answer to this, which is the notion of attractor reconstruction. I'm looking at some complicated system, whether it's the internet or imagine some kind of fluid flow, and there are little convection rolls moving around and this sort of thing. What are the relevant coordinates for the patterns that are forming in this fluid flow? Again, like the safe answer is every molecule. That is not very helpful. Right? It's true, but not very helpful. So within the area of dynamical systems, we got interested in, there was a hypothesis that in turbulent fluids, there were these kind of complicated solution sets, chaotic transients and all that kind of thing, chaotic attractors. So there are methods that will let you take a single observable from the system and reconstruct a multidimensional state space. So there is actually a kind of an objective answer to your question, despite all what I just said about being subjective, which is the subjective thing is certainly true when you approach a new system. Your discipline, you have all these assumptions you bring to interpreting what you're going to look at, the kind of questions you're going to ask. In that sense, subjective. But once you sort of fix that sort of thing, there are ways of pulling out the intrinsic coordinates for the system, and we'll talk about that. In fact, in an interesting way, the entire spring quarter is an elaboration on this idea of reconstructing the sort of intrinsic coordinates of a system. Where's the information stored in the mass? That kind of thing. So,
Interesting.
okay, so exegesis on state space here, right? So the first thing you have to do is figure out what the state space is. For the pendulum, it was sort of an odd space, right? It's a sphere, so two of the coordinates, right? There's a vector. The state vector is 4 numbers. 2 of those numbers live on a sphere, surface of a sphere, and 2 were basically just the real line, R2 together, right? So you have some funny states, but you kind of have to imagine in your head, I got a sphere, sort of a cross product with a plane, right? The velocities live in the plane and then the position, but it's this 4-dimensional space, kind of strange. At every position, location on the sphere, the XY position, there'll be an attached plane that gives the velocities. So we're going to have to do a little bit of this sort of visual, graphical thinking about the structure of these systems when we do this. But that's kind of the first step, and we'll do this, on the homeworks and so on. Okay, so now we have this notion. You might think of this is the instantaneous notion. The pendulum is moving, and I go, where are you? And I have to list out 4 numbers: 2 positional, 2 velocity. That's the instantaneous description of the configuration of the system. The state space is the set of all those configurations, but of course now the system's behaving. So the second equally important component is this mapping we call the dynamic, that takes a state at the previous time to a state at the next time. So the way we think about that is imagine 2 copies of the state space, sort of at time t and at time t plus delta t. And this dynamic is a mapping from this space, current state, to the state space, the next allowed configuration. So we think of that as a mapping. Which obviously, if we want to think about the geometry of this mapping t, now we're in, for the pendulum, we're in 8 dimensions. So already, even for a simple system like this, this is sort of the Faustian bargain of dynamical systems. It's very visual, it's very geometric, but you have to get comfortable with thinking about structures in different dimensional spaces, which we'll do, and we will come up with a number of techniques that reduce the dimensions so we get some more visual, direct sense of what these structures are. But in principle, these things fairly easily become high-dimensional. So, some examples, just to stay familiar. One kind of dynamical system, or I sort of talked about, would be those that behave in continuous time. In other words, differential equations. So I'm using here, we have a state x that's in some space, n-dimensional space. Just think maybe Euclidean space, or maybe like the pendulum, it would be the sphere cross R2. And then the right-hand side is some kind of function of the current state that says what the rate of change of the state is going to be. Right? I'm using Newton's notation, dot is d dt, right? So the rate of change, so a differential equation, the continuous time differential equation says that the rate of change of this vector is a function of the current state. At time 0, we compared the system to the initial condition. That was me holding the pendulum bob off to the side. And then again, there's some mapping from the state space at time t to that at t plus delta t. Right? So that was some mapping. And it's a vector value function, right? Returns the value of as a function of the n-dimensional state, it returns the different coordinates of the state the next time. We call this n here the dimension of the system, whatever we're using. But there are also other kinds of time-varying systems. You don't have to think about continuous time. You can also think about discrete time. And then there are a number of systems. Did you get the space bar? Sorry. Where the evolution the state doesn't change over infinitesimal time, but over discrete time, large jumps. So an example of that would be, turns out that the fraction of the United States population that has measles in March is actually one of these discrete time dynamical systems. And you can actually partially predict and partially at least understand some of the unpredictability of it by writing down a quadratic f here, where x is just one-dimensional, it's just a fraction of the population. And that is a seasonal. Every 12 months they measured the Centers for Disease Control measured this, and it turns out, and we'll come to it, this f here is called a logistic now. It's a quadratic function of the fraction of the infected population the previous season. So that's an example of a discrete time, right? The states, you're kind of stroboscopically looking at them every 12 months. Another example would be, say, for example, neural spike trends, right? So you put your electrode on the axon of a neuron, and what you see are these spikes. And the sort of information is encoded in the time intervals between the spikes. So what you have is a series of events, interspike interval 1, interspike interval 2, those are discrete things, and then the value of it is a continuous number. So that's another kind of discrete time dynamical system. You can think of other things. Now, I introduced this also for practical reasons. This is one way we can study some of these complicated chaotic behaviors in lower dimensions, not having to go to 3 and 8 dimensions, is to look at behavior in discrete time systems in just one state space dimension. But the idea is still the same, and this geometric picture is still just the same. State space, and we have some mapping of the state into itself from previous time to next time. It's both for the same thing, and we'll kind of shift back and forth between talking about differential equations, behavior changing continuously with time, but to illustrate a point, I'll just jump to it, this discrete time one-dimensional map to kind of make the idea really visually clear. And we do that in dynamical systems, hop back and forth all the time. Okay, so now, just again, this is a little bit, this is not the way the Strogatz book talks about dynamical systems so much. This is not trying to emphasize kind of the visual character of this. So there's a way of thinking about differential equations very directly and visually. So what we're going to do here is let's go back to the first order differential equations, a set of equations here. So the rate of change of the current state is a function of the current state. Now what we can do here is, to build up this geometric picture is, let's just imagine we have a two-dimensional dynamical system, right? So its state, vector, has two components. Okay, and we sort of imagine that, so now we have this, we're in R2, each point is a state, and to understand the action of the differential equation, we imagine that there is a vector attached to each state that tells us where to go in the next instant. Okay, so this is kind of the vector field view of a differential equation. Okay, and you can just, if we have this differential equation, well, I can think of, dx dt as delta x over some finite change delta t, and rewrite this equation this way. So which says, here I am at the current moment in this state, and this differential equation over a finite interval updates the state to this new state, x prime, which is the previous state plus some change. Right? The magnitude of that change depends on how much I've course correcting time here, but also this f on the right-hand side of the differential equation. And we have these two different components. The component functions determine the change in x1 and the change in x2. All of which is just to justify this picture. And this is the way we're going to think about differential equations. In other words, just to say it, two-dimensional state space. Every point is a possible configuration of the system, the state. And attached to every state is a little vector that says the next instant you're going to go over here, you're going to go over here, you're going to go over here. So either I could give you a set of differential equations in symbolic form, or I guess a truckload of vectors. Basically, a differential equation is also a list of possible states and a list of rules for how to change states.
Is this one R3?
What's that?
Is this one R3 because the coming towards
this
you?
is artist conception.
Okay.
R2. It might be. I think it's still R2 at this point. We don't know what goes. Yeah, just speeding up to. So. Okay, so what's the benefit of this? I mean, in a sense, I just kind of argued maybe it's visually kind of simple, mostly because we can look at it as the two-dimensional vector field and get some idea of where the behaviors are going. But it's also a more verbose way of describing it. For every state, you say how it changes. Well, one of the benefits is that we can now kind of recast what we mean by solving a differential equation geometrically. So here, what we do is to solve the differential equation, what we do is, here's our initial condition, and the simulation algorithm is nothing other than, look up the arrow that's attached to move to that state. Where am I now? Look up its rule for change and do this and do this. So now we think of this, what we call a trajectory, starting from some initial condition and going to some state at a later time, big T, as simply following the rules in succession. We just follow the arrows. Now, if this is a differential equation, the solution here, the arrows are always tangent to it, tangent to the curve, tell us how to change. So now we have this notion of a trajectory and what a solution looks like. Sort of more directly, what we talk about is the time t flow, and that's actually a mapping. It takes us from the initial condition directly to state at some time t later. Okay, so either we can list this trajectory, which is a time series of states, changing, 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 which would be a long list, or if we get lucky, and this only happens sometimes, like for linear systems and some nonlinear systems, we can write down a function that I plug in the initial condition and the time, and it directly gives me the state, big T later. That's actually that's what we mean by having a closed form solution. And so when before I said these chaotic systems don't allow closed form solutions, what I mean is this time t flow mapping. It might exist, but it can't be sometimes even well approximated. So we'll see some examples of this. Okay, so that's the sort of setting of dynamical systems. State space, dynamic. In the case of differential equations, we can appeal to this visual intuition of a vector field. We now have a notion of a solution, which is just sort of following the rules. And then the solution itself is this time t flow, a mapping from here to here. Right? The system would be predictable if I could write down, like for a simple harmonic oscillator, right? I have x dot is equal to minus x, y dot is equal to get the sign wrong. Simple harmonic oscillator, I could do it in a vector field more easily. There the solution is in terms of trigonometric functions. So for any time, if I have sinusoidal behavior, I can plug in a time, I'll get the state out. So that's an example of a closed form solution. We will do the simple harmonic oscillator. Okay, so that's sort of the basic idea. Now the other maybe more important twist in dynamical systems is that, again, we will, but we don't really want to solve these nonlinear differential equations or nonlinear mappings. What we're going to do is ask about how the vector field or the mapping operates on sets, kind of study the geometry of this. So kind of a critical point about dynamical systems is that without solving classes of equations, it actually comes up with a categorization of different kinds of behaviors that are sort of abstractions or abstractions of notions of equilibrium and oscillation and unpredictable behavior. So there's actually a hierarchy which we'll go through. So the way I'm going to present the kind of results from dynamical system will be in a series of classifications. What kinds of behaviors can you have? Are they stable or unstable? So the key starting point in this classification system is the notion of invariant set. So here's our state space, and we have an invariant set. I'll denote that with a capital lambda here. The idea is very simple. Under the action of the dynamic, or the flow, time t flow, this set, think of it as like a candidate. That set comes back to itself. So the contrast here is the way you would traditionally approach solving a differential equation would be you would specify this zero-dimensional point, the current state, the initial condition, and try to write out some sort of solution that would tell you where it's going for all time. Instead, what we're going to do, we're going to look at sets and see how those sets get mapped into each other. The first case is just an invariant point. So here, this is just a cartoon, as you can write down. We look at this a little bit, a set of differential equations in 2 dimensions that would implement this vector field, but we're kind of getting rid of the equations of motion for now. We're just going to think about vector fields. So here, all the vectors are pointing in. The further away, the larger the vectors are, so you could come in fast and sort of slow down. But the point here is if you start here at lambda, there's no arrow. The arrow has 0 length there. You're not going anywhere. So if you start there, you stay there. So that's an invariant point. Zero-dimensional set, that's an invariant. That's what lambda is, it's going to come back to itself. Another example in R2 would be invariant circles. So again, I've drawn, imagine I sort of first draw this circular vector field, purely rotating. And what are the invariant sets here? Well, presumably there's a point in the middle, if you extrapolate, just so we'd have a fixed point. But now each one of these circles gets mapped into itself. In fact, any circle of any radius gets mapped into itself. And the entire plane is an invariant set. So here's an example where we have a zero-dimensional point that's an invariant set. I probably should draw that. We have one-dimensional circles that get mapped into themselves, and the whole plane gets taken into itself. And that's a very helpful thing. We can start to probe these systems with different dimensional subsets, and it starts to tell us a little bit about what the behaviors can be.
Are we using this for all t or for a specific t?
Right. So we can ask this for any number of t's. Right. Yes. Right. In this case, it could be any number of t's. That will depend on the actual system. So what I'm giving you here is basically for any t. Right. It could be that I could kind of imagine sinusoidally modulating the vector field, so I could only every some period pi or something, it would only map, the curves will map back onto themselves. So you could add. Okay, so now we have this notion of invariant set. We can go one step further and talk about attractors, and this is how dynamical systems talks sort of geometrically or abstractly about stable behavior. So these attractors, again, they're subsets of the state space. They're invariant sets. And if you start in this invariant set and you kick yourself off out of the set, the vector field pushes you back in. Right? So these are attractors are stable invariant sets. They're mapped into themselves, they're invariant. So here, going back to that fixed point example, so here's this point. If I start there, I stay there, but notice, a cartoon picture, we can do some simulation to show this. If I were to jiggle the system, knock myself off, notice that all the vectors are pointing back in, so it'll restore itself. And the way we think about that is the fixed point is this zero-dimensional set. Imagine I made all possible epsilon perturbations in any direction of some size. That'll be this larger set, and I can imagine the vector field operating on that set, and the whole set will collapse back down to this. So we start with the invariant set, we make what we call the vicinity, and the vicinity as a set gets sucked back onto that zero-dimensional fixed point. So again, this is a kind of a visual way of thinking about what stability is. So that's a stable fixed point. Now, the previous example, simple harmonic oscillator example, where we had that concentric set of invariant one-dimensional circles, those are invariant sets, but they're not stable. If I had a circle maps into itself, well, the one just epsilon away maps into itself. So if I start with the first one, I perturb myself, I'm not coming back to where I started. I'll be on a different invariant set. So that's not stable in this sense. But here's an example of an invariant circle, again, the cartoon picture of a limit cycle. So I'm drawing here in black is the set that maps into itself. But now I've drawn a vector field that not only supports that circular invariant set lambda, but if I start outside, all the vectors point in. If I start inside, the vectors point out. Check for stability. Imagine I had some perturbation off to the outside. The vector field is going to restore that. So the whole time I'm sort of following the arrows. That's the solution. You come along, you kick the system, it goes whoop like this, and the vector field restores that, brings it back. Same thing here. If I get kicked inside, take a little energy away, say, the vector field is going to push you back out. So the simple harmonic oscillator is not doesn't have attractors, but this so-called limit cycle is an attracting periodic set. Periodic in the sense that the state is something like a statistical limit cycle. And these really actually weren't discovered, or at least clearly articulated, until the 1920s by this Dutch radio engineer, Balthasar van der Pol. And he was studying heartbeat rhythms. Mathematically, but also experimentally. He was, at the time, they didn't have transistors, they had electron tubes. And so he made, I got the beautiful instruments, the pictures in his papers are quite nice, mahogany boxes, but inside, and he had little pictures of hearts drawn, with lights flashing, but inside were these electronic tubes, oscillators, that he could hook up in the feedback loop and produce these stable oscillations. But the practical thing that he was looking for, though, were oscillators that were stable. This is the earliest days of developing radio technology. And radio technology, the way you broadcast signals is to have a carrier wave. So you need some reference frequency signal that you can impose, say, the audio on top of. So what he was really looking at here was trying to come up with electrical circuits that gave stable, parameterized, tunable frequencies to use the basis. He also appears to be the first experimentalist to have discovered chaotic behavior. In 1927, he's got this nice article to Nature. It's a letter to the editor, and he's talking mostly about kind of operation in radio circuit design called frequency demultiplication. If you impose your voice onto a high frequency signal, how do you get the low frequency audio signal back off of it? Using one of his tube oscillators. And he draws a diagram in there where he's talking about, if I vary the imposed frequency, I get these various kinds of lockings. I'll show you some pictures in later lectures. But in his diagram, he has this little hash mark. And there's one sentence in the paper that says, well, as I was tuning the circuit, and he was only listening to it, they didn't have oscilloscopes, he's listening to it, irregular noise is heard. If you go back and rebuild his circuit and simulate it, it's chaotic behavior. In his paper, he says, but that's a subsidiary phenomenon. The most important thing was this frequency demultiplication, so kind of missed the key phenomenon. Let that do this. Okay, so, right. So, in this sort of quick overview of the basic ideas in dynamical systems and trying to justify this visual way of thinking about nonlinear systems, idea of an invariant set, of a stable invariant set. These are all, you might call them semi-local. We're kind of focusing in some region of the state space. We have our fixed point and talk about stability. We look at some neighborhood around that. But we're also interested in a bigger picture. Namely, what about the whole dynamical system? Right? There's this big state space out there, and I want to basically find out what the interesting structures are in the whole state space. So this is, now we're stepping back and looking at structures sort of further away from these invariant sets. So there's a notion of, when we look at the entire state space, of for a given attracting invariant set, all of the states that lead to it, that's called the basin of attraction. So again, just cartoon picture, now these will all be familiar, but we're focusing now on the larger scale architecture of the state space. So here we have our stable fixed point, and I've colored in brown here all the points that would lead down to this. Over here, if I start initial conditions over here, I'm going to end up on this limit cycle. So the blue signifies all those states in the state space that go to this limit cycle. Okay, so again, so the basin of attraction, it's that set of points in the state space, such that if you started them in forward time, you end up in the attractive invariant set. And as I'm trying to indicate here in the cartoon, there could be many different attractors in different parts of the state space. that themselves have different character. Stable equilibrium with fixed point, or some kind of oscillatory behavior, or something else. So now, when I give you a dynamical systems, one of the things I want to know is where are the invariant sets? Once you kind of list those things out, then what are their basins of attraction? Okay, there's sort of the next idea here is called the separatrix, or basin boundary. It's basically that part of the state space that's not in any basin. Here, so it's just this boundary here. So these are states. If I start there, well, maybe I hop around inside this set, but I don't go to the blue basin or to the brown basin. So what we're trying to do here, again, geometric ideas that help us detect geometric structures and subspaces that sort of constrain the behavior in a very general way. Right? We're not solving any equations here. In fact, the way dynamical systems works, it's really just talking about vector fields and what kinds of vector fields are possible and what sort of sets, invariant sets and boundaries can we produce. Yeah.
So is the separatrix invariant set?
Yes.
Then?
Well, and there can be different pieces of it too.
Right.
So yeah.
Parts of it.
Yeah, I basically giving you just kind of little snippets, and then you can start constructing all sorts of very complicated structures that track. So the net result is sort of the product of this more global view. It's called the attractor-basin portrait. So again, so this is sort of the recipe. Someone gives you a set of differential equations or a vector field somehow, some dynamical system. Sort of the first thing you want to do is figure out where the invariant sets are. Are they stable or unstable? Where are their basins? And then where are the separatrixes? So that's this whole, in a happy circumstance, you can lay out this sort of global architecture of the state space. You've understood a lot about how the system can behave. Maybe you have more particular quantitative questions for some application, fine. You may want to actually know what the basic frequency is here. But if you had this attractor-basin portrait, you know roughly what to expect. Some places I'm going to start, it's going to go to stable equilibrium. Some places it's going to oscillate. There'll be places along the boundary where even small variations will lead to huge changes in the kind of behavior. A little bit this way, I'm going to oscillate. A little bit this way, I'm going to go to equilibrium, be stable. So this is really sort of the kind of a basic goal. Is trying to figure out what these attractor-basin portraits are. Now, kind of stepping back a little bit to maybe a more local view again, I want to introduce, again, this is sort of motivated by trying to figure out what structures in the state space sort of guide and constrain behavior. We're going to talk about these submanifolds. So, in the simplest case, I'll kind of introduce the idea by example. We're going to look at submanifolds that split. There's subspaces that split the overall state space into regions that don't communicate in a sense. So the first notion is that of a stable manifold, and these are points that denote that WS, stable manifold of some invariant set. So I've got a fixed point, which we'll talk through here. It could be a limit cycle, whatever. And then we want to know which points in the state space limit to that set in infinite time. So here is a slightly different example. So I have an invariant fixed point in the center, but now I've drawn a different vector field than before. Like what I showed you before was a sort of an absolutely stable fixed point where all the arrows were pointing into it. And in that case, the stable manifold would be two-dimensional, would be the entire real plane. Here, I've drawn a different kind of vector field where along the vertical direction, points are attracted, but in the horizontal direction, states are repelled, they move away. So we have this sort of flow like this from below and then from above, kind of splitting about the vertical. And then the stable manifold, and you have to think a little bit about the definition, is that set of points that exactly go to the invariant set lambda. Notice if I start up here and I'm a little bit off, I'm going to come down and there'll be a little bit of a right-going vector field will pull me away. So in this case, we have this very clean separation into just a one-dimensional subspace. There's just a one-dimensional subspace of points that go right to that fixed point.
So the question, is this like the basin of attraction then? So this given manifold, or how is it different?
Right, so the basin of attraction is for attractors. This fixed point is not an attractor because if I start here and I perturb myself, I'm going to go away. Okay. Right. But now the kind of important point, structural point about this is if I start over here, I'm going to go here. If I start over here, I'm going to go here. It's like this one-dimensional stable manifold cleaves the state space into regions that never communicate. And that's a useful thing to know. If I start over here, I'm going to stay over here. So what we're trying to do is introduce concepts that let us kind of decompose the state space in terms of these boundaries. And there's a complementary notion, just to kind of complete the picture, of an unstable manifold. So again, here's the picture before. Vertically, points come along here. Now the unstable manifold is the symmetric idea. It's all those points, in some sense, that exactly leave your invariant set. Now how do we say that? Well, what we do is we say the unstable manifold of an invariant set is that set of points in state space such that in negative time, they go to the invariant set. So what do I, in this picture, what is negative time? Flip all the arrows. Just change the direction. Which then, of course, changes this picture back to the one I just talked through. So the stable manifold in negative time is the unstable manifold in forward time. Whatever. It's visually pretty simple. Right? The idea is that we have some, here it's just a point for simplicity. The idea is that there's some set of states that will go down to our invariant set and another along the unstable manifold that moves away. So we'll be using these ideas, invariant set, stable invariant set, basins, separate matrices, stable and unstable manifolds to do a kind of architectural analysis of these nonlinear systems. And they will be sort of the substrate out of which we can start to explain how this unpredictable behavior gets generated. They're sort of atomic elements, if you will, of a chaotic dynamical system. So now that was all a little bit sort of abstract, right? Partly, maybe I should have introduced this by example first, which is pedagogically often preferred. However, I wanted to emphasize sort of I didn't write down any differential equations. What we're really talking about were sort of these flows and vector fields. And they're these various structures that emerge naturally, kind of hinting at their generality. But just to kind of nail this down, let's just talk about one-dimensional dynamical system, one-dimensional differential equation. Okay, so x is just a real line, f is just a real valued function, mapping the line to itself. I have this differential equation. In principle, I can actually just integrate it out to get the solution, right? This is dx dt, and I can move the dt over and integrate. So the solution, kind of formally speaking, if I want to know where, if I'm starting at some initial state x0 and I want to know where I am at time t, well, the solution is the initial place I started plus this integral over time of f. Yeah.
So is it the state, the position, and the velocity? So should it be RT?
Right, good point. So when I was talking about the pendulum, I kept mentioning Newton. So physical systems, in the sense of Newton, are described, I should say kind of mechanical systems, are described by positions and momentum, or Hamiltonian mechanics. That's the physics. When we move into dynamical systems, we actually all this stuff is kind of dropping away. Right? I mean, we were talking about the invariant sets. I didn't really put up coordinate axes. In fact, I don't even really care what the equations look like anymore. I just want to know what the shapes are in the state space. So there's this kind of difference. So Hamiltonian mechanics is a subset of this more general class of dynamical systems. And there will be some of them that have positions and momentum paired up. But we're just talking about vector fields now. And there'll be vector fields that don't have that natural interpretation of their coordinates. So, yeah.
Even odd dimensions.
Yeah, right, in odd dimensions even, right? So Hamiltonian systems, you have the position coordinates, and they're always paired with a conjugate momentum coordinate. Therefore, the state space dimension will always be even a number. Here, it could be 7, 12, whatever, doesn't matter. It can be odd dimension, right? Yeah. So we're kind of leaving the trappings of kind of known kind of physics behind by generalizing this. It's a good question. Yeah, in fact, you should keep asking questions about, as we go through this, if there's some sort of discord with the physics you've been taught, you should definitely bring that stuff up. Because this is. Okay, so we're just doing a one-dimensional differential equation. State space is just the real line, just this horizontal line here. Okay, now what I've done, again, this is just to kind of make it visual, I've graphed f, the right-hand side, some function here that's some cubic. Actually drawn by hand, so it's not really a cubic, right? It looks sort of like a cubic. And then what I did is I projected f, this cubic function, back down onto the state space and attached arrows. Just a few to show you. Wherever f is negative, that means the vector field is pointing towards negative x. Wherever f is positive, the vector is pointing towards positive x. If I start over here, I'm going to follow the x's because f is positive. Starting here, the initial condition, x is going to move this way. If I start here, x is going to move that way, just following the arrows. Okay. So, let's see what this sort of architectural view of the state space is in this simple one-dimensional case. This is going to be complete, again, graphical analysis, no equations or integrals up my sleeve. We'll just go through and say, okay, what are the invariant sets? Again, you can kind of just read this off graphically. What's an invariant set for this one-dimensional system we're drawing? It's wherever x dot, the rate of change of x, is 0. That is where f is 0. And that is where the curve crosses, where x dot is 0, wherever f crosses. So wherever the intersections are in that cubic curve, those are going to be fixed points. Okay, because x dot is 0 there. Okay. Now, which are stable, which are unstable? Again, you can kind of read this off. Look here at x prime. Notice that if I kick myself positive, the vector field is pointing this way, it gets restored. If I kick myself negative, the vector field is pointing this way, it gets restored. Notice that the slope of f of x is negative here. That's associated with the stability of this fixed point. These are point primes. Ditto for x double prime, same argument. Kick myself towards positive x, the vector field restores it, kick myself down here, it comes back. Origin is kind of interesting. Right? If I start there, well, x dot is 0. But if I perturb myself just a little bit away, I'm going to flow away. Positive x, perturb myself negative, is going to flow off towards negative x. So that is an unstable fixed point. Not an attractor, so sometimes we refer to propellers. Okay. So there are our invariant sets. What about basins? Similar kind of argument, right? So what's the basin of x prime? It's the set of points on the real line that go to x prime in infinite time. Set of initial conditions. And that's the whole negative real line except for the origin. If I start here, I'm going to stay here. But if I'm an epsilon away, then I will go to x prime. So that's the basin of x prime. Similar argument for the basin of x double prime. The positive real axis except 0. Okay. What's the separatrix between these two basins? Well, that is in fact the origin, x triple prime. So there, just a graphical way of going through that one-dimensional differential equation that we have. We've listed out all of the relevant sets. Now, maybe I could have given you analytical expressions for this and all that, but actually, this picture didn't take too long to argue through it, and we pretty much know how the system's going to behave. There's not much else to say here. I mean, there might be some particular quantitative thing in an application you need, but in terms of the qualitative picture of what can happen for that dynamical system, that's it. That's the story. We also have stable and unstable manifolds. So the stable manifold of x prime, basically just the basin here. Same thing for x double prime. The interesting thing is now the origin, x triple prime, it's unstable. So it has an unstable manifold, which is the interval between the two stable fixed points, but not including them. So that's the unstable manifold of the origin. So that's it. Kind of sort of complete classification. Now you might actually we went through this example, and one could complain that, I wrote out the formal solution for that one-dimensional differential equation, and all it required was integrating f of x over some time interval. And if f is trigonometric functions or some polynomial or whatever, you can do that. So there would be no point to doing this because you, in fact, could solve it analytically. But the point is that these basic structures we're talking about become very, very helpful. They get, more complicated but interesting in higher dimensions. They're going to be the kind of the basis set, as I said, for trying to explain how these systems can be unpredictable, give rise to complicated behaviors. So that's really the point of introducing this different set of ideas, more abstract ideas about behaviors, because they'll be very handy in higher dimensions. So, any questions? Okay, that's it. See you Tuesday. Hopefully